So far, we've learned how to do a one-way, fully randomized ANOVA. And then we learned to control for individual differences using that randomized block ANOVA. What we're going to learn now is how to do an ANOVA when we have more than one independent variable. This is sometimes called a two-way ANOVA because we're going to have two independent variables. Our dependent variable is going to stay consistent. We're always interested in yield, which makes it much easier to compare these models that we've been building. So we know that yield changes based upon certain factors. We want to dial in which of those factors has the most influence. Here's our setup. To determine whether certain types of beans grow better in specific locations, Juan plants 3 types of coffee bean plants in 3 locations that vary on their altitude and climate. So given that, we can determine which test we are going to use. To select the appropriate test, let's look at our research design. We have 2 independent variables. The first has 2 or more groups, that's factor A, that is the location in which we plant the beans. The second independent variable, which also has 2 or more groups, is factor B, that is the type of bean being planted. But because we have 2 independent variables, we may also have an interaction. Do certain beans grow better in specific locations? Our dependent variable is always going to be yield. It's something that is measured at the scale level and can be quantified as a mean. So what is this research design going to look like? Well, first of all, we have 3 locations. So you notice that we have 3 different types of soil. That's based upon what we know about the climate. For instance, ancient grounds is low altitude and cool. Equal exchange estate is low altitude and warm, slightly different soil. And purgatory plantation is high altitude and cool. Those are 3 different conditions. Factor 1 is location. In this case, we're going to be planting our 3 different types of beans in the same way as we did with our one-way ANOVA, where we have 1 type of bean in each of the poles for our design. So factor 1 is location. We're going to plant 5 poles for each of these examples. So for instance, at ancient grounds, we'll have 5 plantings that look like this first example. What we're going to be able to answer is whether there are differences among the 3 beans that are grown in 3 different soils. Let's take a look at sources of variability that we have for these raw numbers. Number 1, our factor of location is going to be identified by these means for the multiple replications. So these 5 replications at ancient grounds gives us an overall difference, regardless of type of bean, of 9.27. I said difference, it gives us the mean of 9.27. For the replications, all 5 of them at equal exchange estate, we get a mean of 10.67, and for purgatory plantation, 10.07. Those means are different, but are they statistically significantly different? Is there a difference in yield based solely on location without consideration for type of beans? Our second factor is the type of beans that were planted. Ignoring location, are there some beans that grow better than others? We can see those mean differences here at the bottom of each of our columns, 8, 10.73, 11.27. But what's of most interest is whether there is an interaction between these 2 independent variables. So let's review our sources of variability. We're looking for, is there a main effect for factor 1? Do the locations differ in terms of bean yield? Forget about type of beans. Is there a specific location where the beans grow better? Main effect number 2 has to do with the type of beans or type of plants. Do they differ in their yield across all of the locations? The third thing that we're interested in, and most interested in, is an interaction effect. Do some types of plants have a higher yield in one location where other types of plants have a higher yield in a different location? For this example, because we're planting 5 poles at each location, we have 5 replications in our data. So let's establish a null and alternative hypothesis. We're going to assume that the locations and type of beans all are just a wash. There's no difference. So h sub 0 colon mu1 equals mu2 equals mu3. Really what we're interested in is there's no main effects and no interaction. Nothing is happening in our model. Our alternative hypothesis could be written as h sub 1 colon mu1 does not equal mu2 does not equal mu3. All of these saying that there either will be differences or will not. Our null says no difference. Our alternative says that there will be a difference. And so with that, we can select our criterion for statistical significance. And that's going to be easy. We're going to keep our alpha level set to 0.05. And because f is a naturally one-tailed test, we're only looking for changes in one direction. So it doesn't make sense to talk about one-tailed versus two-tailed tests here. We can follow up with our post hoc test to find out which groups are higher or lower than other groups. That's where the interesting findings will come from. The degrees of freedom will be established for each of the sources of variability. We have variability due to factor A. So the degrees of freedom for factor A will be A minus 1, where A equals 3. That's our 3 locations. The degrees of freedom for A is 2. The degrees of freedom for factor B, or type of bean, remember we're planning 3 types of beans. B equals 3, giving us 2 degrees of freedom for factor B, type of beans. The interaction degrees of freedom is A minus 1 times B minus 1. We've already established that both of those are 2. 2 times 2 equals 4 degrees of freedom for the interaction. Our error term includes A times B, and then we're going to multiply that by R minus 1, where R equals the number of replications, which in this case is 5, giving us 36 degrees of freedom for error. Add all those numbers together, you get the degrees of freedom total, which is always n minus 1, 45 cases, and n minus 1 is 44. Once we know the degrees of freedom, we can calculate critical values. Here, because we have so many different sources for our degrees of freedom, we can calculate critical values for each of the factors and the interaction and so forth. We're only interested in the interaction at this point. If we don't have a significant interaction, we don't really find much. So let's calculate the degrees of freedom for the interaction and then use that to get our critical value for the interaction. We have 4 degrees of freedom between, 36 degrees of freedom within, giving us a critical value of 2.634 for our interaction. Now we have our complete setup. We know our factors, we know what we're looking for our interaction. So now we are ready to calculate the test statistic, and for that we're going to return to Excel and the analysis tool pack. Go to the Data tab in the ribbon and click on Data Analysis. In our data analysis box, we're going to be using 2-factor with replication. And then click OK. As we've done before, we're going to select our headers and the raw data and nothing else. So select C3 to F18 for our input range. Rows per sample, that's number of replications. That'd be 5. We're going to keep our alpha level at 0.05, although that could be changed if we chose to do so. And for the output range, click on the output range radio button and click C23. Click OK. It'll cuss at you, and then you can click OK and get our findings. Now it's important to note that Excel can only do balanced ANOVA designs. What that means is, as long as our groups all have the same number of replications, we can do this factorial ANOVA in Excel. However, in the real world, it is not at all uncommon that we will have different numbers of replications. Maybe some of the plants die and we just had to remove them from the data set, or we had to make some other change. There's always slop and error and randomness that occurs in the world. Therefore, if we're going to do this type of complex ANOVA design in the real world, we're probably going to want to use R or JASP or SPSS, because Excel is pretty limited in what it can do with this particular design. Let's take a look at our findings. We are first interested in the factor 1 main effects for location. We can see the means for each location. For ancient grounds, the mean is 9.27. For equal exchange estate, it's 10.67. And for purgatory plantation, it is 10.07. Those means are different, but are they statistically significantly different? To answer that, we're going to look at our ANOVA summary table, and we see for sample, which is the location factor, a p-value of 0.32 non-significant. What that means is there's no significant main effect for location. All of the beans grow the same no matter where they're grown. Well, that's kind of a disappointing finding. You plant whatever you want, whatever location, it all grows the same. But there's a lot more going on, and we're not going to be able to see that unless we start looking at the interaction between these factors. So let's look at our second independent variable and see if there's a main effect there. The second main effect is for the type of beans. So we have Arabica, Robusta, Liberica. Those all have yield rates of 8, 10.73, and 11.27. So what that means is we have a statistically significant difference for type of bean. We see that Robusta and Liberica are growing about the same. Arabica, not as good. Well, didn't we find that out with our one-way ANOVA? That the two more robust beans grow a little bit better and Arabica has a little lower yield? We already knew that. So yes, there is a main effect, but that's not very interesting either. To find the interesting effect, we're going to have to look for the interaction. In fact, anytime you have a statistically significant interaction, you can simply ignore the main effects because they're not going to tell us very much. Here are the findings for the interaction. Our p-value, 0.000, that's a small probability. Our f-value is 22.88. That exceeds our critical value. We do have a statistically significant interaction between type of bean and location. But before we do any more interpretation, let's get our effect size. Let's go back to our Excel spreadsheet. We're going to look at the critical value effect size tab. Scroll down until you find Factorial ANOVA. We're going to get the information that we need to fill in this table by going to the Factorial tab and selecting everything from sum of squares for the sample down to the F critical total blank cell. Highlight, select, copy, jump back to critical value effect size, and paste that information into our table. You will notice there are multiple effect sizes. Which ones are we interested in? Well, the main effects are not of interest at this point because we have a significant interaction. Let's focus just on the effect size for the interaction, which is a 0.71. That's a big effect size for our sample. A more modest 0.66, which is still quite respectable in the population. We're going to report the partial omega effect size of 0.66. So how are we going to interpret these findings? The best way to do that is to look at a graph. Let's plot all of these data points and see what's actually happening. However, we can't do that in Excel. So for that, we would have to turn to JASP. Now, rather than doing that right now, I'm just going to show you what the results would be when we do this in JASP. We're going to interpret the slope of certain lines to determine what that interaction is telling us. But in order for me to help you interpret, I want to go back to something that was confusing to me when I was in grad school. They would show me charts and say, oh, look at this, there's an effect. And I didn't know what I was looking at. Let me walk you through what you need to know for interpreting these types of line charts. Here we have two time frames. That's x1 and x2. So what's being represented here is just a difference in time of measurement. We'll call that before and after, or comparing two different groups. We see the first measurement is 10, the second measurement is 10. Was there a change? Not at all. When you see a horizontal line, that means Nothing changed. It was the same at the end as it was at the beginning. Group 2 was the same as group 1. When you start seeing a slope, now there is a change. But just because there's a slope doesn't mean it's a significant change. Here I have 10 as a starting point, 9 as an ending point, but you can see from these error bars that the error bars capture the other mean. There's really no difference. There is a small, non-statistically significant difference, but it's not anything to be excited about. When you see changes such that the error bars at the second measurement are not capturing the mean of the first measurement, such as this drop from 10 to 2, now you're seeing a significant change. In this case, a decrease from x1 to x2. So the first thing we know is measuring that slope, looking at the difference between the two measurements, that is going to give us an indication of whether there's a main effect or a change. When I measure two effects, or two measurements, two groups, two independent variables, I can plot them on the same graph. And here I'm looking for whether the lines are parallel. In this case, we had an increase from 12 to 13 for our first independent variable. Our second independent variable, or second group, jumped from 10 to 11. The lines are parallel. That means there's no interaction. And they're not a statistically significant change. So when you see parallel lines, that means the groups haven't changed differently than each other. They both went up a little bit, but not statistically significantly. It's when you see the lines getting out of parallel that we're starting to get evidence for an interaction. In this case, the first group jumped from 12 to 15, whereas the second went from 10 to 13. Now, we have a little bit out of parallel here. The groups are changing. They both have a main effect. So we do see an increase from measure 1 to measure 2, but we see they're changing in about the same way. So we don't really have an interaction. We just have a main effect. It doesn't matter what group you're in, you're going to change in exactly the same way. In this example, however, we're seeing non-parallel lines that are going in different directions. This is where we're getting an interaction. The first group, B1, dropped from 15 to 8. There's a statistically significant main effect of a drop there. The second group went from 6 to 7. It's probably a non-significant main effect there. But what we do have is an interaction. It works, our treatment works for B1 group, but it doesn't work for the B2 group. Now group membership matters. Whatever it is that distinguishes B1 from B2, it works for one group, doesn't work for the other group. When you see the lines cross, now you have a really interesting interaction. The B1 group has a statistically significant main effect. It drops. The B2 group has a statistically significant main effect. It increases. We're going to ignore the main effects, however, and report the interaction. Whatever treatment we're doing increases one group and decreases the other group. The groups perform differently. That is a statistically significant interaction. So now let's apply that to what we can see from our picture of what happens with the growth or the yield for our types of coffee beans based on location. Let's start with the ancient grounds location. When you see the dots in similar locations close together, that means they're about the same. So what we're seeing is mediocre growth here at the low altitude, cool climate location. Where something interesting is happening though at the equal exchange state. What we're seeing is two groups that grow really well here and one not very good at all. Robusta and Liberica grow best at low altitude and warm, but Arabica grows the worst. Arabica beans grow the best at high altitude, cool climate. The others are still the same mediocre outcome as what we saw with our first ancient grounds location. Where should we plant different types of coffee beans? We should plant the beans where they grow best. Where is that? We can see that with our interaction. We should plant Robusta and Liberica beans at the low altitude, warm location That's where we're going to get the highest yield from those two. But we're going to grow Arabica beans at high altitude, cool climate. That's where we'll get the best outcome and yield from the Arabica beans. So now we know something that we couldn't see from just main effects. The interaction shows us the complexity of this, and that gives us ability to make much better decisions. Now we're going to get the best yields from all types of beans because we're going to grow them in the proper location and we're going to get the outcome that we're really interested in. So now we can interpret the results and write up the findings. Well, we know that there is a statistically significant difference. We see that both in our test statistic and in our p-value. There is a difference, and we've used our follow-up test to determine where those differences lie. This is what our ANOVA summary table would look like when we do our write-up. And if you'd like to see the full APA-style write-up, you can find that in the class notes. So now we know how to measure one independent variable using a one-way ANOVA. We know how to control for independent variable individual differences using a blocked ANOVA. And we know how to look for interactions using our factorial ANOVA. We started with the very basics, and now we have a good skill set for measuring different kinds of variability with our analysis of variance. Thanks so much for being here. I'll see you guys next time.